So here they are, the two-dimensional shallow water. And you already worked with the same equations, but only in one dimension. We only had the first of these equations, which is the momentum equation in the x direction, and it only has one force. It's this one here on the right hand side, is the pressure gradient force associated with the sloping sea surface. This eta here is the sea level elevation. G is acceleration due to gravity, and this is the associated pressure gradient, which causes an acceleration. And the acceleration is on the left-hand side. On the left-hand side, it says the rate of change of the velocity component u. T is time, u is the velocity. So now in two dimensions, we have another similar equation for the velocity component v, the second equation here, and there will be an acceleration, a change of v, if we have a force in the y direction. So this one is the pressure gradient force that arises from a slope of the sea level in the y direction. The third equation expresses volume conservation. A volume conservation whereby the capital H here is the total water depth. And so here you have a horizontal divergence of volume transports. And if these terms are not zero, then the sea level changes over time. Okay, so these ones are the so-called shallow water equations, and the so-called nonlinear terms are ignored, but we talk about nonlinear terms later on. So this is sort of the framework, okay? And again, I say it again, what we're talking about are horizontal currents, which are depth invariant. So they are the same over the entire water depth. Okay, shallow water equation.